Okay, so I will start again. Okay. Okay, so let me clarify. I want to clarify one thing. So I said that when I said way back when that let's go back to the slide. So in this slide, I really want to emphasize. This. So I have a couple questions. It's not that they when I say that feed-forward nets have not been successful, it's not that they don't work. I really want to emphasize this. If you go into Torch or Piano or whatever, and you have some data, and you take you just take a feed-forward network on MNIST or something like that, and you optimize it, the thing will work. I mean, you'll get a decent test error, right? It's just that if you look at your data and you use the structure from your data, you can probably engineer something better. So I want to make this super clear. When I was saying this, it's not, this line is important. It's not that fully connected nets don't work. The second part I think is important. You can almost always do something better by kind of understanding your data correctly. Okay, so, so now I gave you a couple examples of why you might want to input a set of things, and I'm going to give you the first example of a machine that eats sets of vectors and the thing, and it's the dumbest one. It is a bag of vectors or bag of things. So if you have a set of vectors and you want to get a vector out of it, you can just sum them. So this is kind of dumb, but it's also surprisingly effective in a lot of situations. So it's very important if you're going to do a bag of vectors that you use domain knowledge to pick a good featurization. In other words, however you got the vectors from your data needs to be kind of decent. And let's skip this second line for now. So bags are kind of primitive and blunt, but they are actually effective on a lot of tasks. And that can be considered an indictment of the task if you want. In some sense, bags should never be the best thing because, as kind of we talked about before, you really should preserve the structure in your data. And if you're just taking the sum, you're probably throwing a lot of the data away. So I think and I'm going to keep saying success in quotes, in air quotes, because it's not exactly a success. I think the success of bags on certain problems is kind of a failure of us to be able to do something better, rather than the fact that bags are really the correct answer. Nevertheless, I do want to spend some time talking about bags, and probably actually the rest of this lecture, we're going to talk about bags, which seems kind of weird because they're super primitive. But actually, again, you need to, whenever you do anything, whenever you kind of do anything where you could use a bag of words, you should try it because it's a good baseline. So one thing to make clear, a lot of times people use the word bag of blah to mean a set of blah. I'm going to say set of blah to mean set of blah, and bag to mean a sum of vectors. I may slip and say bag of words sometimes. When I slip and say bag of words, that means a sum of words embedded as vectors. So here I will be, when I want to mean a set, I will say set. Bag means sum of something. So, I mean, I guess where I'm from, that's a reasonably standard terminology. It's not a standard terminology everywhere. So, again, I'll write empirical successes of bags, and I'll put successes in quotes because you can't do it. So, these are all kind of boring in a sense that they're all kind of cheating in a bit ways. So, recommender systems. So, for example, you have at Facebook we have a bunch of users and we have a bunch of posts, and you wanted to say which post, which user is going to like which post. There's a lot of posts or images or whatever, right? And so let's say there's a billion users. There's trillions of images and posts and things. So you don't want, if you want to do a recommender system like the normal matrix factorization way, you don't want to have a kind of a vector for every single post that's independent, right? You don't want to have a vector for every single image that's independent. You may want to parameterize the posts or images or whatever. And a simple way to do it is a post is a bag of the people who liked it, or an image is a bag of the people who liked it. So this is a pretty standard practice, and it's super effective and super cheap. So you might imagine there are more subtle ways to kind of take a post and make it into a vector. But what you find is that seriously large scale, you don't have time for it, and it's a good idea to just be stupid and pick a bag. Another example, which again this is a lie, is generic word embeddings like word2vec. So if you think about what word2vec does, for example, the CBOW takes a context as a bag and predicts the middle. That's a lie because it has kind of a little bump shape on it, but it works almost as well if you don't do that bump shape in the middle. So in other words, you have your sequences of words, and you take a sequence of 5 words in a row, you actually sum them and then output a, so again, you sum them with a little bit of a weight around the center, but whatever. If you were to sum them flat, it wouldn't be that much worse, and then you would have a bag for predicting the thing. Let me come back to this one in a second, because I think this is there's more of a lie there, but I won't come back. So a third place, again, it's very similar to this one, where you see bags being kind of not bad, is a lot of language processing, natural language processing tasks of the form of kind of sentiment analysis, or especially retrieval. I want to find a sentence that's like my sentence in a big pile of sentences. Bags are super effective here. They're not always state-of-the-art. They're quite often a little bit worse, but they're not a lot worse, and they're much, much, much cheaper than, for example, an LSTM or a complicated RNN or something like that. So depending on your computational budget, it may be much better to do something stupid and lose 10% accuracy than do something smart and take a lot more compute. And a lot of times they just end up being better anyway. So again, I think retrieval is a good example where it's just better. And so you can see, this was an ICLR paper where you can see lots of places where just taking a bag was really the best thing. This paper is predicting hashtags from posts, and again, like content may have been tiny bit better, but bag was right up there. And bags are super fast to train. Like if you want to train, if you just do word embeddings with a bag, it's super fast. Let me go back to this one, because it's a bit of a cheat, and I think it's an important thing to recognize. If your goal, when you are optimizing something with word embeddings, is to solve a task, you might want a complicated architecture. But if your goal, when you're making word embeddings, is to use the word embeddings for something else later, in fact, if you want the word embeddings to kind of have all the information about the data, you want as crappy a model as possible, because all the information needs to be in the word embeddings and not in the model. So in some sense, this one is the middle one is different than the other two, because this one is just about efficiency, essentially. Well, no, it's about generalization as well. So in some sense, these two are a little bit about generalization, but this one is really, the architecture is that way because really that's the best architecture for the task. If you want generic word embeddings, then all the information should be in the word embeddings. That means the model should be as simple as possible. Let me show one more, again, a success, and I'll put it in quotes because it's not exactly a success, it's just a failure of us to do better. This is Bole. Joe did this when he was a intern at Facebook. I have it up somewhere. Okay, so let's see if I can. So you can go to his webpage and look at this. So this is the VQA data set from Virginia Tech. That came out last year, so it's partially Microsoft, partially Virginia Tech. And it's not that many, it's some maybe 100,000 images, some hundreds of thousands of questions. It's not super huge. And usually when you train on these things, you train on ImageNet, a ComNet, and then you do something with the words. So let's pick an image and then type a question. So the images refresh randomly, so I don't know, here's a picture of. Can someone ask me a question and I'll ask it, and we can.
What is this?
Oops. Okay, I cheated. Let's see if I can go back and get that same one back. No, I cannot. Okay, so I'm sorry about that. Let's try again with. Okay. there's no way I'm going to be able to get that exact image back. Okay, sorry. Let's try one more time. See if we can find one with a training in it. Okay, here's another one with a training in it. Okay, so let's. Where is this one? Okay, so train station, great. So this one, it did really quite well. So here's the image. You say, where is this? It's the train station. Great. This is split out based on the image only. If it just looks at the image, the thing says, well, that's a microwave. If it looks just at the words, where is this? It says kitchen. These are important. This breaking out by the things are important. So let me say first what the architecture is. The architecture is dead simple in a sense, and it's pretty complicated in a different sense. So the architecture is, you take the image, you pass it through a ComNet, and it's a ComNet that was trained on ImageNet, I think VDG. I don't actually remember now which one. And you take the final output layer, or one before the full connect layer, and then you project it down to a given dimension. And then you take a bag of words of the question. So you don't have any information about the order of the words or anything in the question. You just take a bag on the question. And then you just do a softmax against all the possible answers that were in the data set. That's it. This is really quite dumb. And sometimes it does quite well. So let's pick something here. I don't know. Let's break it. So first, this might not break. Baseball, yeah, it didn't break. So is this baseball? So it should say yes, right? And in fact, it doesn't. It says pitcher. Terrible. Okay, so first you can already see how bad the system is. So actually, if I said, what sport is this? It said baseball. If I said, is this baseball? It says pitcher. There's only so these things are extremely so. There's several interesting things here. The first interesting thing is this is an incredibly stupid architecture in a sense. The second thing you might think is, well, but the ComNet is really good. It's getting a lot of information from the ComNet, right? Actually, it turns out, so this thing gets a performance of about 55% correct on the test questions, 55, 56. So ComNet plus bag of words gets 55, 56. State of the art on this task is like 60% now. That even may be a bit high. So you get just a tiny bit more with very complicated LSTMs and things on the questions. Just a bag on the questions does just as well as, and all sorts of complicated attention on things does essentially as well as this, which shows how kind of bad it is. The second thing is, the thing I want to emphasize about that is, so I say 55% correct out of 60. If you use just the words, if you use just the bag of words, you don't even look at the image, you get 44%, right? So without understanding the order of the words, without seeing the image or anything, almost all the performance is already there. The bag of words from the question tells you everything. And the reason why is because people ask the same questions over and over again, and people answer the same questions over and over again. And there's so few of them, essentially, that if you just answer the head, you're doing pretty well on that 44%. And this is biased in all sorts of crazy ways. And you'll see this whenever you make a data set like this. Is there a cow? There's clearly not a cow, but it will say yes. The reason why it says yes is because when somebody says, is there, they're not going to say no, just because that's the way the labelers work. The data set is massively biased towards yes. It likes yes a lot more than no, because that's how people answer the question. And it can get that from the bag. So when I say this is a success of bags, I'm saying in quotes because on one hand, it's just picking out the biases in the data, which is in some sense a success because that's pretty much all we can do right now. Again, 55 to 60%. That's all the gap between like very complicated processing of the question and just summing everything. But at the same time, it's an absolute failure in the sense that, well, clearly we could probably do better. There's all sorts of other biases, like it's really biased towards tennis. So this is clearly not a sport. Oh, too bad I lied to you. Okay, so I promise if you go yourself and play, you'll find that all sorts of things that are not sports, if you ask what sport is this, it'll say tennis. So this time it's at skateboarding, I don't know why. It's really too bad. So in general, the thing is super biased. it has all sorts of guesses just because that was what was in the data set. The bags picked that bias up, and that's the thing that is incredible about bags. They pick up a lot of amazing biases that you think, wow, I can't believe that, you know, I really was able to get all those statistics just by summing the words and getting them out. Yes?
So here you the back of the word embeddings.
Yes?
The word embeddings have been trained offline before today, or?
This one, I think they're actually back propagated through. I think the word embeddings are actually pushed to the task. So the COMNET is trained offline, and then the projection matrix is trained for the task, and I believe the word embeddings are trained for the task. We also tried with word embeddings, random word embeddings, and literally random word embeddings. We also tried with word effect, whatever. Didn't really change the results that much. But I think this one is back off to the words. Okay, so I don't know. This is in some sense a triumph of bags because, well, you're doing almost state of the art with bags, but in some sense it's a kind of defeat for what we can do, I think. So again, the surprising thing is, why is this moving without me? So the surprising thing to me was, so one thing that you might think is, oh, it just does really well with the bags because the image features are so good. And the surprising thing to me was so much of the performance comes from the question, and like you get just this extra 10% from the images. Even though the image features are really good. The image features are really good. Okay, so again, I think this is in some sense a triumph of bags, but also notice there's another cheat here. So in all the examples I gave, there was a cheat. And the other example is, you know, the image features were not a bag at all. They were a COMNET, right? That's not a bag by any means. Okay, so let me talk a little bit about why bags can do so much, like why bags can count. And so basically what I'm going to do is the like 3-slide or 4-slide version of compressive sensing. Have you guys seen compressive sensing before? Okay, so basically RD is really, really big. And when you sum a bunch of things, you can get them back. Like the sum just keeps, it didn't matter that you summed it, you can get them right back again, right? So let's call the D-sphere SD and the ball BD. So again, in this notation, the boundary of the ball of dimension D is SD minus 1. So SD has the same dimension as BD, but it's not its boundary, right? Okay, so we're going to suppose we have a set V in SD. V is N. This is our dictionary. This is our embedding, our word embeddings. Okay, so we're thinking of V as our word embeddings. We're going to suppose that we have N words. And this last bit is a bit of a cheat, but we're gonna do some back of the envelope calculations, so we need to make our lives easy. So we're gonna assume that our word embeddings are ID uniform on sphere. That doesn't happen in kind of learning settings, but whatever. Just for the calculation, just to get a sense of how big things are, we'll do that. So again, V is our word embeddings, and what I'm going to show you is that you can take S word embeddings, and as long as the dimension of the embeddings isn't too small, you can get the word embeddings back from the sum, which might be surprising to you, I don't know. It's somewhat impressive. It says RD is so big that when you sum the thing, then there's only, even when you had kind of a lot of choices, there was only one way you could have made that sum, essentially. Okay, so when you're in RD, the most basic classical how big is RD fact is the inner product of two random vectors has small, right? So if you have two vectors, uniform vectors on the sphere, and you take their inner product, it's like 1 over root d in expectation. The proof of this is very simple. Since inner product is rotation invariant, just make one of them be delta on the first coordinate, right? And then the other one had norm 1, so in expectation, the first coordinate has norm 1 over root d. That's it, right? So you take two vectors and you take their inner product. It didn't matter where the first one was, so you just rotate the thing like this, so it's up at the top of the sphere, and ta-da, you see that the coordinate is 1 over root d, right? So that may not seem impressive to you, but if d is, if d is 500, everything is almost orthogonal, right? That's pretty, 1 over root 500 is a pretty small inner product for two random vectors to have. You can make this statement even stronger. So in general, in kind of, whenever you see something has a mean of something, you say, well, what's the deviation from that mean, right? And say how quickly does the law of large numbers happen? And here, your deviations are pretty small. So the probability that two vectors have inner product bigger than A is less than 1 minus A squared to the d over 2. So if A is like 0.5, then this is like 0.75 to the d over 2, which means very quickly the probability is tiny that you're the probability that you're close to somebody else is tiny, tiny, tiny. Again, we're on the sphere, so inner product is almost the same as distance, right? We can prove this, so I'll steal a proof. Actually, I don't know who invented the proof, but I saw it in Roman Roshinen's notes. So, quick proof of this. Actually, I won't prove it. Let's just keep it here. You can look in Roman Roshinen's class on what's called concentration on. So this property that the sphere random points on the sphere are far apart is called concentration of measure. And this statement is actually what's really concentration of measure. Because what this says is if you look at a d-sphere, all the area is in a band around the equator, right? The cap is tiny, comparatively. This says that the cap is exponentially small in dimension. So all the masses in the... So another way, it's really too bad there's not a board there. It'd be super nice if there was a little chalkboard there. But what this says, another way, if you kind of rewrite this a little bit, what you can say is... sorry? Oh. Oh. Yeah, I don't know if this is a good idea. Okay. Okay. I'll use it one time, and then I will never, ever, ever do this again. So, so the real, you can take that statement there. So you have your ball, right? And what you can do is say, give me some set, whatever. Give me some set on the sphere. And here we're on the d-sphere. So you've given me some set with area A. And so let's say this set, let's call it P. So P is this cap, right? And let's suppose P is equal to whatever it is, A. Then you look at P, comma, epsilon. So P epsilon is a fat net by epsilon, right? So even if A is really tiny, P epsilon, you can use that to show that P epsilon covers pretty much the whole sphere when epsilon is tiny. And how big does epsilon need to be? Well, you get it from that. I mean, it needs to be exponentially small. So a tiny, tiny fattening of any little set covers the whole sphere almost in high dimensions. This is called concentration of measure. This is the statement of concentration of measure we'll use. Actually, the proof of it, you can prove this in one line, but I didn't write it, and I don't want to do it on that little board. So, but there's a nice geometric proof. Go look in Roshinnen notes. It's, in some sense, the exact form of this is, whatever it is, but from this statement, a statement like this is reasonable, right? Because what you expect is things to concentrate around the mean. And the mean is here, so if you put 1 over root d there, everything will work out. Okay, so this line is important. You take any two random vectors, the probability they're bigger than A is smaller than this number, which decreases exponentially in b. Okay, so we've been given these n vectors v, which are word vectors. They're uniform on the sphere, and now I get a bag. I get x is equal to sum over these things of v. And the question is, how big does d need to be so we can recover the indices just by finding the nearest neighbors, right? So let's see how. This is the dumbest recovery algorithm ever. I'm just going to take all my word vectors. I'm going to take my bag and say which one is it close to. And the ones that it's closest to, I'll say, well, those are the things that were in my bag. How big does d need to be for that to actually work? If you try this in R2, it won't work, right? If you take 5 points on the sphere or 10 points on the sphere and sum them, there's no way you're going to be able to get back, say 5 out of 100 on the sphere in R3. There's no way you're going to be able to figure out which one it was just by finding the nearest neighbors. It's going to be somewhere in the middle. In RD, you can. On the D sphere, you can. So if it were true that the inner product between every one of the guys in our sum and every other random guy is like 1 over s, then we could do it, right? Because then the nearest guy, then the sum over them is less than 1 of random guys, but VT against X is roughly 1. The reason it's not exactly 1 is, you know, these have some interference with each other, right? But again, not much. So as long as this guy is less than 1 over S, when you sum them against guys outside the universe, outside of these, well, you'll get sum of inner products less than 1, right? So this is all we need. We just need V transpose. We just need V that's not in our set against some V that's in our set to be 1 over S for every V that's not in our set and for every S that is in our set. So how likely is that? So remember this, that's the same formula from before. Whoops, I can't point to my screen, sorry. Instead of that A, we have that S, right? We just replaced it. So we'll say, suppose we want epsilon probability of failure, then epsilon looks like this. I'm going to go through these really fast, and I apologize, I couldn't understand it if I were in the crowd, and I was up here saying this fast either, but I'll put slides up and you'll see it. But really, this is the kind of this calculation you can, once you kind of sit down and think about it, you can do it. It's not a super hard calculation, right? It's very hard to sit and watch it, I understand. I won't spend too much time. The point, what I want to get across is how little there is to it. So we're just going to say, we denote the probability that some guy is too close by epsilon, so that's our failure probability, right? And again, our failure probability, we just want to make sure that all the word embeddings that were not in our set are farther than 1 over s from somebody in our set. By farther, I mean inner product is smaller. So we'll just bound like this. So that's just taking the union over all the events, right? So basically, I just say, here's one of the events, and here I have ns of the events, so I just take the union over all of them. And then now we do our first estimation. Like when you have something to the ns, roughly, that's like ns times that thing, right? Like this is just this. This is just the higher order terms die out, right? So this is expanding out this product and just keeping you keep the one term and then the next term after it, and all the other ones we ignore. So you get the ns. The ns comes from here, from product. And why is this thing here? Okay. Okay. No, come on.
Full screen.
Okay, there we go. Okay, so this ns was doing the product. Then the next step, you just use the approximation for logarithm. Logarithm 1 plus x is kind of like x when x is small. So you just follow that through. And again, I couldn't follow this if I were sitting in your place. I just want to say that the things we're using is that the product of things, you can just take the first term, and then we use log of 1 plus x is kind of like x when x is small. That's it. And then when you rearrange everything, you need d is greater than s squared log ns over epsilon. Log of something over epsilon looks scary, but log of 1 over epsilon, come on, it's a log. It grows super, super slow, right? So for a very low probability, yes?
So here you are using this recovery algorithm that is based on just the k.
Yeah.
Let's say that you do L1 recovery. So
You can do better.
then you would expect S log. Sorry, you would expect S.
One side. Give me one side. Give me one side. Okay. Actually, we can even do it with the nearest neighbors. We can get that thing. So what he's complaining about is there's a square here. That square is ugly. I don't like it either. That's unpleasant. That's not what we should get. But at least, up until now, we've done nothing fancy, and we got, D is s squared log and s over epsilon. So my claim is that this term is essentially a constant. Log is a constant function. I don't know if anybody's ever told you that, but it is. Log is constant, and it's actually a pretty small constant. So let's say it's 100. So basically, you need whatever the number of things in the sum, whatever the number of words in the sum, you need roughly that many dimensions, that number squared dimensions to recover. Actually, you don't need the squared. So he's pointing out the squared is terrible. Where did the squared come from? The squared came from the fact that I wrote 1 over s. I need this inner product to be 1 over s, because I did the dumbest thing. I just summed up the absolute values. But we assumed that the guys were uniform on the sphere, so actually the signs will alternate, right? And so when you have ID variables that are alternating, actually when you sum them up, you get root of the number, not the number. So if I was a little bit more careful up there, then everything would have been a lot messier, but I would have gotten s instead of s squared. That's the only place where you do that, just because I ignored the alternating thing in the sum. It's still slightly worse. I don't think they usually have an S. Like when they do the concussive sensing, they don't have an S in here. So I just did this, whatever. Either I made a mistake, or I can't remember exactly whether, but I'm pretty sure they don't have an S here if you do this carefully. But I didn't think it was worth it. Sorry?
That's a very small part.
Exactly. So I didn't think it was worth getting rid of. So I don't know. I'm sure you can get rid of it. But the point is, this is tiny, right? It's essentially the sparsity. Right? Basically, if I have a bag of 5 things, and I want to recover those 5 things with the dumbest algorithm on the planet, just find the 5 closest things to the bag. Ta-da! As long as d was bigger than the 5, well, 5 and some change, right? Then it comes back. And actually, I checked for like probably 1 in 1,000. If d is 5, I think you need like 50 dimensions or something like that. Now, of course, in real life, your word vectors were not ID on the sphere, so this is bullshit because, you're learning something, so a lot of the things will be closer together, and your life won't be that good. But it is roughly true, and you can try it, that you can actually recover from bags. So for example, when you do something like word vector or something like that, it's often quite true that there's a contrastive term, right? So it's not as spread out as uniform vectors, but things are spread out. Almost every time you use word embeddings for something, somewhere in there's a contrastive term. So things may be clumped up a little bit more than they would be if they were completely covering uniformly, but they're pretty spread out. If they weren't spread out, you could have used the lower dimensional space and not lost anything, essentially. There's a huge literature on this kind of bound. I think the applied math people went nuts about this over the last maybe 10 years, and there's literally thousands of papers on these kinds of bounds. Usually you don't do something as stupid as finding the nearest neighbor. You solve a lasso problem, and then you can get the answer. Actually, I don't even think there's a. I think this is even. You can do much better if you're more careful. I wasn't careful. This was just to show that roughly the idea is simple. There's a lot of space in RD, and if you take a bag, you can get the things back pretty stupidly. So, as I was saying, that there's a huge literature on this, and people solve a lasso problem to do it. Actually, if you look at the solving of a lasso, you can write solving of a lasso, if you look at ISTA or a lot of other kind of subgradient descent methods. If you unroll them, they look like a neural network. And actually, you can use a neural network to do the recovery. It actually works pretty well, right? This is, so Cray, Kaplu, and Macario and Ranzato had a paper like 2008 or something like that, and then Carl Greger in 2010 says, okay, look, let's just optimize a neural network to do sparse recovery, and it works super well. It's actually really good. So the interesting thing here is that if someone gives you a bag of words, and it's not such a big bag, say like 10 words, you can embed it in a reasonably small dimension, say like a couple hundred, and a neural network, a reasonably shallow neural network, can give you back what the elements in the bag were from the bag. Right? So this is something important to remember about bags. You're summing it up and it's super convenient, but the information about what the elements of the bag is still there. So when you're talking about retrieval, so I said bags are super good for retrieval. Bags are super good for retrieval because it's like retrieval with synonyms. The word vector tells you, oh, these two words are kind of close to each other. But actually all the information about what words were in that bag is still there, up to some synonyms. Right? Okay, so, of course, when am I supposed to stop? 3-4 minutes. 3-4 minutes? Okay, so I'll stop later. So, let me talk a little bit about the failure bags, and then I'll say what we'll start with tomorrow. Because up until now, I think we've been talking about the negative things, and then we're going to talk about like the positive things. So, bags didn't solve vision. I mean, convolutional nets. I want to make it super clear. So I think when you're doing your NIPS paper and there's an opportunity to use a bag of words or something like that, you should do it, and you should be very careful about it because it's a super strong baseline. But frankly, bag of words are stupid, and they can't solve hard problems that require kind of understanding things. Convolutional nets, I think, are a great example of this. Back in the 2003, 2000, whatever, people were using bags of SIF vectors, and it did something. It's not absolutely terrible, but it's a lot worse than a connet. So, throwing away all the structure in the bag, again, you can still do something with it, and it's actually pretty cool because when you just do bag, you can train that on huge data. But at the same time, you lose so much compared to keeping the correct structure, keeping the correct kind of multi-scale compositionality. And there's lots of other things. I mean, bags also do badly at kind of NLP tasks. I think translation is a good example. Like, you can imagine when you're translating something from like English to French, the order is really consistent, right? So it's a shame to throw that away. You should keep that order as you're going. So it's not like bags solve the world, but try it. It's amazing, especially if you have, in two extreme cases, where you really have a lot of data or where you really have a tiny bit of data. In the first case, because it's a small model, and in the second case, because you can it trains super, super fast. And of course, you can't solve everything fast. Let me say what we're gonna do tomorrow, because I'm not gonna go into it. I just wanna advertise, because I feel like I sold you guys short. I've just told about really, really simply. I kind of talk about bags, which is boring, and we want to talk about something more exciting. So tomorrow we're going to talk about kind of attention and kind of memory network type things. Things that instead of taking bags, they look sequentially through your data and kind of do multiple computational steps. Or things like graph neural networks that you give it a set and it passes in parallel through it, kind of communicating as it goes. And you can do much, much, much more sophisticated things than bags. You can actually do things that eat a set, but keep kind of some extra structure along with them. Okay, so I'll stop and take questions. Yep.
Yeah, I was a bit surprised that you were able to do such a good job with bags on the visual question answer,
Yeah.
because it ignores the syntax of the show picture of a dog biting a man, and
Yes.
is the man biting the dog?
Yes.
And you said yes.
Well, but how many times do you see a picture of a man biting a dog?
No,
It's all about the bias.
but so it just means that your evaluation set doesn't evaluate what you want it to evaluate.
So this is a complicated question. I partially agree. So this is actually a huge debate in everywhere I go, really. But because the question is, what is it that you want to measure? I mean, useful things if you want to do something useful, a lot of times it turns out that the bias is the most useful thing. Like the head is actually super useful, right? So the head being, if you have a distribution, the head means this part, not that part, right? And the head, you can often figure out the head from counting. You make a big, stupid model, and by counting I mean just doing really stupid statistics like bags and things. So you can often get the head from stupid statistics. And you can say, well, that doesn't get the subtleties of whatever and all these, but that's 90% of the questions are that. So it's unclear whether that's bad. It's good because it gets 90% of the questions. And actually you see this a lot of times. People come up with really cool ideas for architecture, really cool ideas for machines, and then they try and test it and it doesn't work. Why? Why doesn't it work? Because 90% of the questions were easy and you just had to count. And the interesting ones, you had to kind of collect a huge scale. So building data sets that actually test, understanding of things is ridiculously hard. But yeah, I think it's a super fair point. It's, in some sense, a failure of the evaluation criterion.
Any other questions? Okay, so let's thank Arthur again. So we have a really fast break because the next lecture starts at 2 p.m.
So I heard someone mention once that in this very high-dimensional space, you can actually input exponential number of vectors that are almost orthogonal.
Yeah, that's what that said. That was exactly that thing. So if you look at the statement,